ABCI++ is the handshake between CometBFT consensus and your Cosmos SDK application. From proposal creation to validation, execution, voting, and commit, application callbacks shape what becomes a block, and they must do it deterministically, safely, and predictably. We've already built the foundation: Cosmos architecture, CometBFT, ABCI++, and then SDK modules, keepers, stores, messages, and testing. Now we connect that application knowledge to consensus by following how CometBFT drives each phase of the block lifecycle. CometBFT drives consensus: networking, validator coordination, block agreement, and finality. What it does not define is what transactions mean or how application state changes. That belongs to the app. ABCI++ is the contract between the two, where CometBFT calls into defined phases and the application returns decisions: proposal contents, accept or reject results, app hashes, and vote extension data. This boundary keeps consensus deterministic while giving the application more influence before a block is finalized. Think of each block as moving through 5 responsibilities. First, the proposer builds a candidate block with PrepareProposal, choosing and ordering transactions from the mempool. Next, every validator runs ProcessProposal to decide whether that candidate is acceptable. Consensus voting determines whether the network agrees on it. After agreement, the application executes the block deterministically through FinalizeBlock. Finally, commit persists state and returns the app hash that consensus will trust at the next height. During proposal construction, CometBFT gives the current proposer's application a candidate set of transactions, along with limits such as maximum block size and block context. This is the proposer's chance to apply application-specific policy: choose transactions, reorder them, drop invalid or unwanted ones, or inject required transactions. That freedom is still bounded. The prepared block must satisfy consensus constraints and remain acceptable when the rest of the network later runs ProcessProposal. Once a proposed block is gossiped, validation becomes local, but consensus critical. Each validator passes the same proposal to its own application through ProcessProposal. The app checks proposal-level rules, transaction structure, block limits, and anything that would make the block unsafe to commit. Given the same state and proposal, honest validators must reach the same answer. Accept keeps consensus moving. Reject should be rare, deterministic, and reserved for clearly invalid proposals because disagreement can stall the chain. After consensus finalizes a block, every honest node must execute it the same way and reach the same new state. The application starts with begin block logic, such as handling evidence, scheduled actions, or per block setup. Then transactions are delivered, anti-checks run, messages execute, gas is accounted for, and writes are staged. End block logic follows with module updates, such as validator changes or distributions. In ABCI++, this execution is routed through FinalizeBlock. Commit is where executed changes become durable application state. The application writes those changes, computes a Merkle-style route, and returns it as the app hash. CometBFT carries that hash into consensus-visible block history, so every validator must produce the same value. If execution was non-deterministic, hashes diverge and consensus safety breaks. That commitment is also what light clients, state sync, and later audits rely on. At a high level, ABCI++ separates decisions by risk and timing. PrepareProposal is local to the proposer. Choose transactions and shape the candidate block. ProcessProposal runs on validators. Decide whether that proposal is acceptable before voting. Extend vote and verify vote extension. Attach and check vote metadata without replacing block execution. FinalizeBlock and commit are where deterministic execution and durable state changes happen. Keeping these responsibilities separate is what protects consensus safety. Consensus parameters are the chain's safety envelope. They define what a valid block may contain before consensus accepts it. In PrepareProposal, the app must choose transactions that fit byte limits, gas limits, evidence rules, and validator update constraints. In ProcessProposal, peers apply the same boundaries to reject unsafe proposals. Treat these values as hard protocol rules, not tuning hints. If a proposal exceeds them, both correctness and liveness are at risk. When demand exceeds block capacity, proposal building becomes a policy decision. The proposer chooses from the pending pool using signals such as fees, module rules, dependencies, or MEV protections. But choice is not unlimited. The final block must stay within byte, gas, and protocol limits, and validators need deterministic checks to decide whether it is valid. Strong designs maximize throughput without sacrificing fairness, simplicity, or liveness. ABCI++ code must produce the same result on every validator, every time. Avoid local clocks, randomness, external services, or node-specific files in consensus paths. Impose deterministic ordering before processing transactions, evidence, module logic, or validation checks. Also respect each callback state rules. Know when reads are safe, when writes are committed, and when effects must be deferred. Treat this code like critical infrastructure because one mismatch can reject proposals or stall the network. Not every error in ABCI++ means the same thing. A malformed proposal should be rejected deterministically, not treated like a node failure. Bad transactions should be filtered or rejected with clear logs and metrics. Local application failures need safe recovery paths because panics can remove validators from consensus. The key is to categorize errors before reacting. Fail safely in PrepareProposal, reject predictably in ProcessProposal, and test adversarial inputs so errors stay local. Because ABCI++ moves application decisions closer to consensus, every callback becomes part of the system's safety and liveness story. Safety means deterministic execution, valid state transitions, and matching app hashes across validators. Liveness means proposals are not rejected unnecessarily. Callbacks finish quickly, and validation rules stay consistent. In production, this requires observability around latency, rejection reasons, filtering behavior, commit status, and mismatch alerts. Before mainnet, prove those assumptions with testnets, simulation, fuzzing, and chaos testing. ABCI++ gives the application a deeper role in consensus, shaping proposals, validating them, executing deterministic state changes, supporting votes, and committing results safely. Keep responsibilities separate, respect limits and parameters, and handle errors defensively. Next, we turn this lifecycle into code with proposal handling and vote extensions.